Hello students, welcome back to SGC online chemistry classes. This is lecture number 2 on the topic coordination compounds. Coordination compounds. Coordination compounds. Well, dear students, from the last video, you all have come to know regarding the definition of coordination compound, followed by the very important theory for the first time proposed by a Swiss chemist by name Alfred Werner, who gave the important postulates regarding the coordination compounds. Nothing but complex compounds or complex salts. And in the last class, you have collected the information regarding the 4 postulates given by Alfred Werner in his theory. Before we go to collect the merits and demerits and continued part, let's have a recap over the postulates of Werner's theory of coordination compounds. Well, students, the first postulate says, in the coordination compound, the central metal atom or ion that possess 2 types of valencies, namely primary valencies and the secondary valencies. Postulate number 2, primary valency are commonly non-ionizable. They are non-ionizable and are satisfied by negative ions only, while secondary valencies are recap over the second postulate. Primary valencies are commonly ionizable. Primary valencies are commonly ionizable and are satisfied by only negative ions, while secondary valencies are non-ionizable. Make a correction. Primary valency ionizable, satisfied by negative ions only, while the secondary valencies are non-ionizable. They are satisfied by either negative ions or neutral molecules, which are called ligands. Postulate number 3. So primary valency or valencies which is variable. Primary valency is variable, which corresponds to the oxidation state of the central metal atom or ion, whereas secondary valency is fixed, that does not vary, is fixed, which corresponds to the coordination number of the complex. Postulate number 4. What postulate number 4 says? Primary valency or valencies are non-directional. They were non-directional, whereas the secondary valencies are directional. They are directed in space around the central metal atom so as to give a definite geometrical structure or a shape to the complexes. And in moving further, you can add primary valencies are denoted by dotted lines, whereas the secondary valencies are denoted by solid lines. So these are the postulates pertaining to the Werner's theory of coordination compounds. Dear students, this question has appeared many a times in the examination, and do get familiar with these postulates. Write twice or thrice and you will get familiarity. Well, let's collect in the today's class. Let's collect the merits. Let's collect the merits of Werner's theory. Merits of Werner's theory of coordination compounds. Werner's theory of C.Sir coordination compounds. So what are the merits? This theory explains the formation of coordination compounds, explains the formation of coordination compounds. Second, this theory further explains or differentiates, this theory differentiates between primary valency and secondary valency. Third, it also explains about the structure of coordination compounds. These are the three important merits of Werner's theory of coordination compounds. So what these are? This theory explains successfully regarding the formation of coordination compounds. Second, it differentiates between the primary valency and secondary valencies. And third, it explains about the structure of the coordination compounds. Let's collect briefly some information with example to gain the knowledge idea about the merits. Well, students, Werner, he prepared a series of compounds by taking cobalt chloride or cobalt 3 chloride with ammonia, with a large excess of ammonia. So he prepared a series of compounds. What are the compounds he obtained by the reaction between cobalt 3 chloride and ammonia? Let's see the following series of compounds, nothing but complex salts, nothing but coordination compounds he obtained. The first one, what he obtained was, let me write the formula, CONH3 taken 6 times Cl3. This was the first compound, which was yellow in color. Further, second compound, CONH3 5 times Cl2. This was purple in color. It was found to be purple in coloration. Third, CONH3 4 times Cl2Cl, which was found to be green in coloration. Green. Last compound. So CONH3 taken 4 times Cl, empirical formula is same, Cl2Cl, which was found to be violet in color. Look here, dear students, Werner prepared a series of complexes by the reaction between cobalt 3 chloride and ammonia. So these are the compounds he obtained. Well, students, over this part a question has appeared in the CET competitive examination as, so when these compounds, when the aqueous solution of these compounds, when it is treated with silver nitrate solution, the question is of this kind. When these complexes, 4 series of compounds, cobalt complexes, what he obtained. So on treating these solutions with the aqueous silver nitrate, how many moles of silver chloride gets precipitated, or how many moles of silver nitrate is consumed? Such a type of a question has appeared. Now he noticed further on treating these complexes with the silver nitrate solution and treating all these with the silver nitrate solution, AgNO3 aqueous. So what was obtained for this? For the first complex, 3 moles of silver chloride was precipitated. This was the PPT, precipitated. How many moles of silver chloride gets precipitated for the first complex? So 3 moles of silver chloride was precipitated. For the second one, 2 moles of silver chloride was precipitated. Third, 1 mole of silver chloride was precipitated, and even for the last compound also 1 mole of silver chloride was precipitated. So here you can see when you look into the number of chloride and the ammonia molecule in all the complexes is same, but the amount of PPT, the moles of PPT gets precipitated was different. See what you can see here, Cl3, all the chloride ions which are written outside the square bracket, which are the primary valencies, they get ionized, giving these are going to precipitated with silver nitrate as a silver chloride, white PPT of silver chloride you get. So this question has appeared in the examination. Further you can notice 2 of the Cl2 are outside the square bracket, those only gets precipitated, one each in the complex 3 and complex 4 are written outside the square bracket, they only get precipitated, leaving the other chloride ions in the solutions. They were retained. In the complex 1, all the chloride ions were precipitated. Complex 2, out of 3, 2 gets precipitated, 1 remain in the solution. Similarly, in the 3rd and 4th, only 1 chloride ion gets precipitated, 2 were retained in the solution. So, these complexes, complex 3 and complex 4, the empirical formula is same. They were going to show the isomerism character, one with green in color, another with violet in color. These show isomers. These isomeric in character shows isomerism. So, this was question appeared. How many moles of silver nitrate consumed? You can write 3 moles. How many moles of chloride gets precipitated? 3 moles with respect to 1, 2 and 1 mole each with complex 3 and complex 4. So this is how Werner successfully explains about the formation of the complexes. Second, he differentiated between the primary valency and the secondary valency. See here, all these are secondary. What about primary and secondary valencies? I can write. See the primary valency, the primary valency or secondary valency. I can write primary valency in this complex for the first complex is 3, while the secondary valency is 6. Primary valency for the second complex, primary valency for the second complex is 2. Ionizable valency is a primary valency. Secondary valency is a fixed 6-1. Primary valency for the third complex is 1. Secondary valency is again 6. For the fourth complex also primary valency is 1. Secondary valency is 6. You can notice in all the 4 complex secondary valency is fixed, which was said in the postulate. The secondary valency is fixed, which is not variable. What about primary valency? Primary valency is variable. See, primary valency in the first complex is 3, while in the second is 2. Third and fourth it is 1. So this is what Werner could able to explain or differentiate between the primary valency and the secondary valency. Out of the 6 secondary valencies, all the 6 secondary valencies are satisfied by the neutral ammonia molecules in the first complex. Try to understand. In the first complex, all the 6 secondary valencies, 6 secondary valencies of the cobalt are satisfied by the 6 neutral ammonia molecules. What about in the complex 2? The 6 secondary valencies, out of 6, 5 are satisfied by the neutral ammonia molecule and the 1 is going to satisfied by the chloride ion. That means chloride ion. The chloride ion which can satisfy both primary valencies as well as the secondary valency here. Now, coming to the complex number 3 and complex 4, secondary valency is 6. Out of 6, 4 satisfied by the neutral ammonia molecule and the 2 satisfied by the chloride ion. You can notice here, this chloride ion which was satisfying both primary valency as well as secondary valency. This is how the Werner was able to differentiate between the primary and secondary valencies. Coming to the structure, he gave out a structure for the complex so far he prepared. So what about the structure I can write for the complex 1? So I can write side by there for the complex 1. Observe it. So complex 1, cobalt is the central metal ion, cobalt, and surrounded by the 6 ammonia. He gave out a structure NH3, 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 ammonia molecule, and 3 chloride ions, Cl, Cl, Cl. So the primary valencies are denoted by dotted lines. So this was the structure given out for the complex 1 CO, whose secondary valence is satisfied by the 6 ammonia molecules and the primary valency by 3 chloride ions. This was the structure given by Werner in explaining the coordination compounds, properties of the coordination compounds. This is structure 1. Then what about structure 2? So here itself I can mention for the structure 2, secondary valence is 5 satisfied by ammonia and 1 satisfied by chloride ion. So I can write one of the ammonia molecule is removed out for the second structure. 5, 1, 2, 3, 4, 5. And the fifth one is 5 secondary valence is satisfied by ammonia. 6, 1 by 1 of the chloride ion, I can write solid line. So here the chloride ion, which was satisfying both primary valency as well as secondary valency, which was pointed out. See here, which was pointed out here. This is the structure for the complex 2. If I write the structure for the complex 3, I can remove one more ammonia. So here CO, NH3, 4 times Cl2. 4 out of 6 secondary valency, 4 satisfied by 4 neutral molecules, NH3 and 2. So here out of the 3, the 2 chloride ions were satisfying both primary valency and the secondary valency. This is how the merits of Werner's theory we covered over. There are 3 important merits of Werner's theory. 1, Werner successfully explains about the formation of coordination compounds. 2nd, he differentiated between the primary and secondary valencies. 3rd, which was explains about the geometry of the complexes. Let's collect now the demerits. So what are the demerits of Werner's theory? I can write here itself demerits of Werner's theory. Demerits. What are the demerits of Werner's theory? Let's collect one by one. This theory fails to explain how negative ion can satisfy both primary valency and secondary valency. This was the major drawback or demerits of Werner's theory. He fails to explain how a negative ion, you can see the negative 2 of the chloride ion written in the complex were satisfying both primary shown by dotted line, solid secondary. The 2 chloride ions in the complex mentioned were satisfying both primary as well as secondary valencies. This was not explained how a negative ion can satisfy both primary and secondary valency was not able to explain by Werner. Then second was do not give any electronic interpretation. Do not give any electronic interpretation for the formation of complexes. Werner fails to give any electronic interpretation or electronic explanation, electron involvement for the formation of complexes, for the formation of compounds, coordination compounds. And what was the third demerit? So he fails to explain, did not explain this theory, did not explain about the magnetic and optical properties, magnetic and optical properties of complex compounds or coordination compounds. Werner's theory fails to explain about the magnetic and the optical properties of the complexes. So these are the three demerits of Werner's theory of coordination compounds. Let me repeat the demerits of Werner's theory. Number one, this theory fails to explain how a negative ion can satisfy both primary as well as secondary valencies, as I shown with the example structure. Second, did not give any electronic interpretation regarding the formation of complex compounds or coordination compounds. And third, it did not explain about the magnetic as well as optical properties of the complexes. Now, let collect the important terms, the very important terms pertaining to coordination compounds in next discussion. Well, students, over this terms a question was appeared with weightage of 2 marks in the examination. Let's see what are the important terms pertaining to coordination compounds. Yes, with the title, some important terms pertaining to coordination compounds. C.C. stands for coordination compounds. Let's collect first the list, the terms one by one, and later we are going to discuss those one by one. What are the important terms pertaining to coordination compounds? First one is the central metal atom or ion. Central atom, or usually it is metal, central metal atom or ion is the first term. Second is the coordination entity or coordination sphere. Third is regarding the coordination. Third one is the coordination polyhedron. Fourth term is ligands, also pronounced as ligands. Fifth one is oxidation number of the central metal atom. Oxidation number of central metal atom or ion. Sixth one is the coordination number of complex compound. Seventh one is homoleptic and heteroleptic complexes. Homoleptic and heteroleptic complexes. Well, students, these are the terms one should know with respect to coordination compounds. What are those? Let us glance once again. Central metal atom or ion. Second is coordination entity or coordination sphere. Third one is the coordination polyhedron. Fourth is the ligands or ligands. Fifth one is oxidation number of the central metal atom or ion. Sixth, the coordination number of the complex or coordination compound. Last one is the homoleptic and heteroleptic complexes, and this part has weightage of 2 marks in the examination. So 2 mark question has appeared over this heading. Now let's collect the terms one by one. Very easy, and follow it. First one is the central metal atom. Central metal atom or ion. So how to define this central metal atom or ion? Metal atom, understand it? Metal atom surrounded by definite number of negative ions or neutral molecules. Metal atom surrounded by a definite number of negative ions or neutral molecules, together called ligands, for your kind information. Metal atom surrounded by a definite number of negative ions or neutral molecules in coordination entity. You will get what is meaning of coordination entity in the next term, while getting idea about the next term. In coordination entity is called central metal atom or ion. I repeat. Dear students, look at the term central metal atom or ion. What does it mean? It is the metal atom. It is the metal atom surrounded by definite number of negative ions or neutral molecules, which are called ligands together, In coordination entity is called central metal atom or ion. For example, from the example you will be cleared, you will get a clear idea. For example, so what is this central metal atom or ion in the coordination entity? If I take FeCN6 4 minus, it is the coordination entity. In which the central metal atom or ion. So what is the central metal atom? Central metal atom or ion in this complex is Fe3 plus. Then if I take example another CuNH3 taken 4 times, whole charge 2 plus. Central metal atom or ion, nothing but ion, in this is Cu2 plus. Fe3 plus is the central metal ion in the coordination entity FeCN6 4 minus, ferrocyanide complex ion. Then Cu2 plus is the central metal ion in the CuNH3 4 times 2 plus cypromonium ion in the cypromonium coordination entity. So Cu2 plus is the central metal ion, and in ferrocyanide ion coordination entity Fe3 plus, it is Fe2 plus, not, it is Fe2 plus. Fe2 plus is the coordination in the FeCN6 4 minus, the central metal ion is Fe2 plus. In the further discussion you will come to know how 2 plus Fe2 plus and Cu2 plus you get will be cleared in getting the further ideas. So this is what regarding the central metal atom. I conclude, what is central metal atom? A metal atom surrounded by fixed number of ligands in a way. It is the central atom or a metal atom surrounded by negative ions or neutral molecules in the coordination entity. In this coordination entity, the Fe2 plus surrounded by 6 anions, cyanide ions. In the second coordination entity, the copper Cu2 plus ion surrounded by the 4 neutral molecules, ammonia neutral molecules. So Cu2 plus surrounded by 4 neutral molecules in the second coordination entity. First, Fe2 plus surrounded by 6 cyanide ion, Cn minus ion in the first one. This is what? Metal atom surrounded by fixed number of negative ions as in the case 1 or neutral molecules as in the case 2. So in the coordination entity or a coordination sphere, what is called central metal atom or ion. Now let's collect the next. What is a coordination entity or coordination sphere? Let's take the second one, coordination entity or coordination sphere. In short, let me write coordination entity, which is almost same as coordination sphere. What is meant by coordination sphere or a coordination entity? It constitutes a central metal atom. It constitutes a central metal atom or ion surrounded by fixed number or definite number of surrounded by fixed number of same negative ions or neutral molecules, and are enclosed within a square bracket, are termed as coordination sphere or coordination entity. I repeat. So what is a coordination sphere or a coordination entity? It constitutes a central metal atom surrounded by a fixed number of ligands, same as fixed number of negative ions or neutral molecules, but enclosed within the square bracket. They were written within the square bracket, which are termed as coordination sphere or coordination entity. And on further part, the groups, the ions are groups written outside the square bracket, are called counter ions. Are called what? Counter ions. This coordination entity is non-ionizable, while the counter ion is ionizable. Make it very clear. Coordination entity is non-ionizable. It gives a complex ion. But while the counter ion of the complex compound or coordination compound is ionizable. Let me take this point with example. If I take an example I take a coordination compound K4FeCN6. So what is the coordination sphere in this? For this complex, if I write the coordination sphere and counter ion, what are the coordination sphere of this? The coordination sphere or a coordination entity of this complex is FeCN6. FeCN6 4 minus. FeCN6 4 minus is the coordination sphere or coordination entity of this complex. Then counter ion. What are the counter ions? K plus ions are called counter ions. If I take example 2, same CuNH3 taken 4 times SO4 with respect to this. So what is the coordination sphere or a coordination entity of this second complex? It is a CuNH3 taken 4 times 2 plus is the coordination entity or a sphere, and counter ion is SO4 2 minus. SO4 2 minus. So this is how CuNH3 taken 4 times 2 plus is the coordination sphere, SO4 2 minus is the counter ion. FeCN6 4 minus is the coordination sphere, K plus is the counter ion. So this is what regarding the second term pertaining to coordination compound, which is nothing but a coordination sphere or coordination entity. What does it mean? The coordination sphere or a coordination entity, it consists of central metal atom or ion surrounded by fixed number of negative ions or neutral molecules, surrounded by fixed number of negative ions or neutral molecules, and are written within the square bracket. They are written within the square bracket. Are termed as coordination sphere or a coordination entity, while the ions are groups written outside the square bracket are called counter ions. They are called counter ions. That completes the second term, coordination entity or coordination sphere. Now let's go to collect the third, coordination polyhedron. What is meant by coordination polyhedron? Let's see. Coordination polyhedron. Normally or usually the coordination polyhedrons are Normally coordination polyhedrons are octahedral, square planar. Normally these are the coordination polyhedrons: octahedral, square planar and tetrahedral. What does it mean? So it means coordination polyhedron means coordination polyhedron is nothing but the spatial arrangement of negative ions or neutral molecules, nothing but ligands. Coordination polyhedron is the spatial arrangement of negative ions or neutral molecules around central metal atom or ion in a coordination sphere. I repeat, what is coordination polyhedron? The normal coordination polyhedrons are octahedral, square planar and tetrahedral, shown by the coordination compounds. So how do we define this coordination polyhedron? Coordination polyhedron is nothing but a spatial arrangement of the ion or neutral molecules around the central metal ion in the coordination sphere. Octahedral, if I take M represents the central metal atom or ion, L represents the ligand or negative ions or neutral molecules. Octahedral, in the octahedral, all these surrounded by the ligands. This is octahedral polyhedron of a complex or coordination compound. Square planar, M is the metal atom. Square planar, in the square planar you can have the ligands arranged in the at the four corners of a square planar. Tetrahedral, so M central metal atom and four ligands are arranged at the four corner of a regular tetrahedron. like this. L ligand, 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 ligand. So this L represents ligands, M represents the metal atom. This is how the coordination polyhedron idea is obtained. I complete. We have covered 3 important terms now before we go to fourth one. First, central metal atom. Second, coordination entity or coordination sphere. Third, coordination polyhedron. Coordination polyhedron is nothing but the spatial arrangement of ligands. I can say ligands. Nothing but ions or neutral molecules around the central metal atom or ion in a coordination sphere. This is what regarding coordination polyhedron. This is octahedral arrangement. This is a square planar arrangement, and that one is tetrahedral arrangement of the normal coordination polyhedrons. Now let's go to the fourth and important one term, which is ligands. I hope you followed this. Let's collect the fourth one, which is ligands. Fourth term, ligands or ligands. Ligands are ligands. What is meant by ligand or a ligand, which has appeared in the examination? Ligand, ion or molecule. Ion or molecule capable of donating one or more electron pair to the central metal atom or ion through coordinate bond. Through coordinate bond are called ligands. So what are ligands? Ligands are nothing but ions or molecules which are capable of donating one or more electron pair to the central metal atom or ion through coordinate bond. Are called ligands. I repeat, ions are molecules which can donate one or more electron pair to the central metal ion or atom through coordinate bond are called ligands. Or you can define in another way also. The ions are molecules bounded to the central metal atom or ion. Ions are molecules bonded to the central metal atom or ion through coordinate bond. Are called ligands. Well, students, here we have alternate definitions for the ligand. What are ligands? The ions are molecules which are bonded to the central metal atom or ion through coordinate bond are called ligands. Or otherwise, the ions are molecules which can are capable of donating one or more electron pairs to the central metal atom or ion through coordinate bonds are called ligands. So this is the fourth term. In further, based on the number of electron pairs donated by the ligands to the central metal atom, depending on the number of electron pairs donated by ligands to the central metal atom, the ligands are further divided into monodentate, bidentate and polydentate ligands, and those different types of ligands along with examples and the remaining important terms. We shall collect it in the next video. Thank you, students.